Hi, everybody. Welcome to our first round of IRIS-HEP Fellow lightning talks. We're going to get a quick intro to each of a few of our fellows and what they're going to be working on this summer. First up is Samuel. So whenever you're ready, you can get started.
All right, sounds good. Hi there, I'm Sam Ferraro. I'm an undergrad at Brown University, and this summer I'm working with Simone Pagancriso and Sergo Ginderani on charged particle reconstruction at the Muon Collider. So before I get into exactly what I'm doing on this project, I want to introduce the Muon Collider a little bit. It's a proposed project for a future collider. Here's like a little diagram of what some ideas of what it would look like. That in last year, the P5 report, which is a report from an American Steering Committee on Particle Physics, suggested would be one of the best options to push the energy frontier in particle physics. And the main two reasons for that is that as elementary particles, when you collide muons, all of their energy goes into the collision, which differs from proton-proton collisions like at the LHC, where you have partons and parton distribution functions, which determine how much of the energy is actually going into the collision. And in this graph down here, you can see that if you have a 14 TeV center of mass collision of muons, that probes the same depth of physics as 100 TeV proton-proton collision. So it's a really good way to get much farther out into the energy frontier than we have already. Additionally, muons being around 200 times more massive than electrons experience synchrotron radiation much less, so we can actually accelerate them to these energies, whereas it's much, much harder to do that with electrons. So at this high energy, high luminosity muon collider, we create an abundance of effective vector bosons, making it really sensitive to the Higgs boson, which is very important with modern particle physics, but it'd be a great collider for all sorts of other reasons. The main issue with muons, though, is that they are unstable particles, and so they decay. So you get, as they're traveling in this beam, you get decay particles that travel along with it. Due to the boost of the muons, everything tends to go collinearly with them, at least for a good amount of the distance. Eventually it might spread out, but initially it will go collinearly. And so you get all of these particles, photons, electrons, positrons, neutrons, charged hadrons, all traveling with your beam of muons and intersecting your detector with interesting geometry. And you can see in these graphs here, you get millions of these low energy background particles intersecting your detector with each of these collisions. And this is in contrast to your maybe few hundreds of signal particles at much higher energies, but way fewer orders of magnitude. So you really have to filter out this background, which is called the beam-induced background, the background induced by the beam of muons. So that brings me to actually what I'm working on. So to combat the beam-induced background, your reconstruction algorithm has to be really good, really efficient, really fast. Reconstruction algorithms basically just take the information your detector outputs and try to piece together all the information back into particles. So you have a hit here, here, and here with this much energy. Okay, you have a particle going through that they had this much momentum and something like that. The current reconstruction algorithms are in the ACTS, a charge tracking software format, which runs in a specialized ILC software framework that isn't really able to be parallelized very well. But the new Kiefer-HEP software framework, which is what people are transitioning to away from ILC soft, is very easily able to be parallelized and has very powerful parallelization features. So my task this summer is to move the ACTS tracking software from ILC software, and specifically in the Marlin sort of design, to Kiefer-HEP into this Gaudi framework, which will be able to be parallelized, which is another thing I'll be doing, trying to optimize it and make it able to handle this beam-induced background. So on the side here, I have a few graphs of what I've been working on so far. There's been two versions of ACTS, the old one and the new one, which is within, I think, the last few months. And so I've been trying to get both of these to work with the Muon Collider simulation software. And I've managed to do that with particle guns, so just like shooting a beam of particles at the detector and seeing if I can reconstruct them. And as you can see, they both reliably get very similar results The detector geometry has 14 layers, so it makes sense that it peaks at 14 hits per track, one for each layer. So this is pretty good data here. After this, now I'm going to start transition to moving everything from Marlin to Gaudi, and that's what I'm up to in the future. So thank you. I don't know if we're doing questions, but that's my presentation. Are we doing questions?
Yeah, if there are any, but
Yeah.
First of all, thank you, Sam. I appreciate a nice talk. Any questions for Sam? No, got a hand raised. Jordan?
Hi. Yeah, my question, and I might have missed this, but you mentioned ILC. What is that?
Oh, yeah. So there's these software frameworks. I'm sorry, there's someone doing construction outside my window. There are these two software frameworks. ILC Soft, I think, comes from Specific Collider, but a lot of people use it. It's just like a set of packages and code that you work within so that it makes it easier for you to develop more advanced programs. So ILC Soft is what they were using. IRIS-HEP is what they're transitioning towards, and IRIS-HEP is more modernized and has all these parallelization features.
Gotcha. Thank you.
Yeah.
Okay. Any other questions? All right. Thank you, Sam.
Yeah.
Next up is Sara. Sara, you want to go ahead and share your screen?
Sure. Is my screen visible?
Yes.
Okay. My name is Sara. My project is charged particles reconstruction at Muon collider. So the standard model of the universe has been quite successful in explaining some of the observed physical phenomena. However, there are several phenomena such as the existence of dark matter, antimatter symmetry in the universe, origin of neutrino masses, etc., which cannot be explained by the standard model. So there is a need to look beyond the standard model. Collision energy can be expected to increase by at least an order of magnitude due to the recent technological advances that have taken place. So there is need for future particle colliders in multi-tera electron volt scales that can increase the energy range for direct and indirect searches. One of the ways in which this can be achieved is by building the proposed 100-kilometer long future circular collider, which will collide protons at 100 TeV center of mass energy. There are many advantages to building a muon collider. However, there are some challenges as well. Muons are unstable and decay into electrons or positrons accompanied by neutrino and antineutrino. Another related problem caused by muon decay is that it causes dissipation of the muon beam. After muons decay, they tend to scatter in all directions. Some enter the detector and cause noise. Every square centimeter of the active area of the tracker detector is hit hundreds of times. A muon collider detector faces the challenge of separating the products of the muon collisions from an intense beam-induced background from secondary and tertiary interactions of muon decay particles. A track is an object reconstructed from hit positions of charged particle trajectories. By measuring the momentum of particles, we can reconstruct the particle tracks. Track reconstruction is complicated by the large number of hits due to the beam-induced background. The spatial distribution of BIB hits is different from the hits created by the particles generated from muon collisions. So I would be working on improving the track reconstruction algorithm that we already have. The tracking algorithm helps differentiate the beam-induced background hits from the tracks of charged particles generated by primary collisions. We plan to carry out cluster shape analysis, which would help us distinguish between signal and BIB events. The current tracking algorithm is relatively slow and takes several seconds to process one single event. My project will focus on making it faster and more efficient. I plan to investigate how timing and reconstruction performance of tracking algorithms can be improved by utilizing directional information from specially arranged silicon detector layers in the particle detector. I also plan on working on validating the improved algorithms to ensure that they can be used by all members of the collaboration, as well as explore other ways the algorithms can be improved or optimized. Thank you.
Thank you, Sara. Any questions for Sara? No? All right. Thanks again, Sara. Next up is Alexander. Alexander, do you want to go ahead and share your screen?
Sorry, I had myself on mute. So today I'll be talking about leveraging ServiceX. Leveraging ServiceX to transform PhysLite data into flat N-tuples with systematics. Can you hear me okay?
Yeah.
Okay, just making sure. Sorry. Okay, so the problem at hand, the intended main storage format for Atlas is a format called PhysLite. The issue with PhysLite is that we need to be able to apply systematic variations to data in PhysLite files, but the code to do so is currently not compatible with columnar analysis or the Python ecosystem. One way to address this, at least in the short term, is to run these systematic variations as part of creating flat N-tuples out of PhysLite, which is something we have existing software for, and that software is TopCP Toolkit. So the solution is to encapsulate TopCP Toolkit as a ServiceX transformation, which will access the grid. So we access the grid via ServiceX, and then we run an analysis using TopCP Toolkit all in one. It'll be easy to use. It should work for any system, and it should include any desired data, especially systematic. So what does this look like in practice? So first, what is TopCP Toolkit? TopCP Toolkit, it will take in a PhysLite file, which is like just all the collision all the event information, and then it'll take in a user-specified configuration algorithm or configuration file, excuse me, and then all these parameters like, do you want systematics? Yes, no, and then how many events, and then it'll pass it through. It'll run an event loop over all the events, and then it'll spit out an N-tuple form with nice lists like rows and columns and all that. Okay, and then the second thing I mentioned was ServiceX. So ServiceX is it's a way for Atlas participants to access Atlas data and run analyses remotely. So for our application, we'll have to put TopCP toolkit into an image and then give it to ServiceX. And then all the user will have to do will be to they'll have to specify some TopCP toolkit stuff, then give the configuration file and the location of the files, and then ServiceX will look up the files and then run TopCP toolkit over them, and then transform the files into a nice N-tuples form. Oops. Okay, so to put a transformer onto ServiceX, you have to make a Docker image of your transformer. So that way, so if you don't know what an image is, or a container, excuse me, well, sorry, an image makes a container is made from an image. So a container is like a virtual machine, if you know what that is. Like if you have Microsoft or Windows and you want to run Linux, then you can like install a virtual machine, which will be like an isolated file system that will run Linux on your Mac or Microsoft OS. So a container is kind of like that. It's like an isolated file system, but it's a lighter weight and faster. So we'll be making, or we are making a Docker container, and this that we'll put on ServiceX, and this is like the architecture of it. So the host will be ServiceX. The container will be built from the image that we're writing, and then it will have volumes, which are basically just like connected directories, and that's where the user will specify the input and output files, config files, etc. And then, like the meat of what's going on will be the TopCP toolkit. So just an overview, TopCP toolkit, that's Docker, that's ServiceX, and then that'll be the final project. Any questions?
Thanks, Alexander. Any questions for Alexander? Got a hand raised. Mikhail?
Hi, thank you, Alexander. Just kind of quick question regarding using Docker container. Is that one is something as a required, or you kind of like chose to use it just like for portability reasons? It's kind of like, can you actually communicate with like ServiceX without like setting up the Docker container, but having it on a local machine within other environments?
I guess I didn't make it very clear, but the container will be on ServiceX, so the user doesn't really have to worry about Docker at all. That's just for for development purposes. Because ServiceX, to have a transformer on ServiceX, you have to make the image of the transformer. So that's what we need Docker for. But the user won't have to worry about Docker at all. They'll just have to submit a request through ServiceX. And then
so it's kind of like just a top layer. So it's a layer on top of ServiceX to have that format being used with the ServiceX, right?
Right. Yeah.
Okay, got it. Yeah, thank you.
Sure.
Any other questions? All right. Thank you, Alexander. Up next is Valerie. You want to go ahead and share your screen?
Yes, you hear me well?
Yep.
Okay. So my project, I have named Statistical Treatment of Analysis Branch Challenge Result with RooFit, and my mentors is Jonas from CERN and Alexander from University of Wisconsin-Madison. So first, quick small introduction about Analysis Grand Challenge, which led also to IRIS-HEP. So Analysis Grand Challenge is a realistic environment for investigating high energy physics data, analysis scale when we have high luminosity. So the Analysis Grand Challenge offer a blueprint for high energy physics analysis applications which can be implemented using different tools and approaches. And now it's mostly done with different Py libraries. So like all your analysis you can do in one Jupyter notebook, which is pretty simple and pretty clean. And in the end, as soon as you have all things in one place, it also can be reusable and redone. So my goal consists of maximum likelihood method, which one of the last steps. So right now in Analysis Grand Challenge, it's implemented via cabinetry and PyHF, where cabinetry is used for configuring template histograms, which you use for fitting, and PyHF are used like for fitting. Goal of my project is to add one more implementation which can be used. So people who want to use this Analysis Grand Challenge blueprint, they can choose what they want to use. Either it can be Python libraries or it will be root. So we're going to implement histogram templates via root hist factory, and then we're going to feed this using RooFit. Some extra things which also be good to be added. So cabinetry, we have very, I would say, pretty toolkit, which simplify results visualization. And then you don't need spending much time when you present your analysis results or want to make a pretty picture. So we're gonna also to add this via root, have good pictures. I already have some preliminary results. This is done using Analysis Grand Challenge CMS TT-bar open data example. So in the left part of slide, you can see results which was obtained using PyHF and results which was obtained using root hist factory and RooFit, and you can see they're almost similar. Also, in the right part of slide, you can see fitting results of different parameters, because while fitting we fit not only one parameter, and also a visualization example which already done with root. So that's totally all. Main goal of the project is keep analysis simple and clear, keep it reusable, and provide more ways to perform analysis in fast and efficient way. That's all from my side.
Thank you, Valerie. Any questions for Valerie? All right. Thanks again.
Thanks.
Next up is Andrii.
Yes, hello.
Hi, can hear you. Go ahead and share your screen.
Yes. So, hi, my name is Andrii. I'm from Taras Shevchenko National University of Kyiv. My mentors excuse me. My mentor is Dmytro Belytskyi for this project. And the name of the project is Topological Rare Hadron Decay tagging with deep neural networks. The decay we are studying is key-short to two muons decay, which has not been observed yet and is highly suppressed, making its observation a significant challenge. The most stringent upper limits were set by LHCb, set and published, and our goal is to do better than these last published results. The main obstacles of this analysis is our very weak signal and contribution of several backgrounds, such as double fakes from K-short to pi to muons to neutrinos decay, which is basically the misidentification of pions as muons, and overwhelming combinatorial background. Overall, in this study, we will try to develop some approaches to suppress combinatorial background and to improve the sensitivity of our analysis. To do this, we will use the CMS Run3 data from 2022 and 2023 years. As one of the approaches for training our models, we will exclude from data the signal and double fake regions, leaving only pure combinatorial background events for training, and we will use Monte Carlo simulations for signal part training. Previous machine learning approach we used was XGBoost BDT, which is a commonly used method in high energy physics for signal and background separation. This BDT model helped us to reject combinatorial background significantly. And with that, we had a pretty solid improvement on our expected upper limit. Though it is not good enough, that's why we started thinking on how we can improve our sensitivity further. And one of the approaches is looking into DNNs to find a better way to reject combinatorial background. This will include trying some regular fully connected networks or more advanced models like graph neural networks, or etc. And we will also try not only data versus Monte Carlo training, but also data versus data. Unlike BDT, DNNs are a very powerful computing resource, so we should be careful when working with them. For example, on the slide, you can see that if we will use all kinematic variables, the DNN can easily compute the invariant mass of Kaon, which will lead to cutting the spectrum by mass instead of learning more difficult correlations between signal and background. And here is an example on the plot, how it looks like when incorrectly trained model is applied to data. We can see clear dependence on mass, and it is not good. Further studies are needed to understand how to prevent such biases. It is only one example of what we should consider while working with DNNs. This project will require significant understanding of the physics of our decay, as well as knowledge of not trivial DNN architectures, which could handle our data in the most efficient way. So for the summary, we have the last published upper limit, which we want to improve, to overcome. We will use data from CMS Run3. Several studies were already performed, which increased sensitivity, though it is still not enough. And that's why our goals for this project will be to learn new algorithms and deep neural network architectures, as well as to perform robust studies on topological information of our decay to extract the most informative features and their combinations. And finally, we will develop an advanced model which will improve the sensitivity of our analysis. Thank you for your attention.
Thank you, Andrii. Any questions for Andrii? All right. Thank you. Moving along. Dmytro is up next.
Yes, good evening.
Hello, how are you?
I'm fine. Can you hear me?
Yep, sure, just fine.
Okay, I'm sharing the screen.
All right.
And so it is. Do you see?
Yep.
Yeah, okay. My name is Dmytro, and my mentor is Andrii Len, and I want to present the project usage of CUDA for improving HLT performance. Well, let's talk about the prerequisites. There are in the universe few observable phenomena, such like as gravitational lengthening or anomalies in galaxy's rotation, which can't be explained by existing theory. And this phenomenon implies that there is existing such entity which interacts solely through the gravitational interaction, and so it's called dark matter. Yeah. So how should we fix our theory? So from the perspective of the particle physics, we can make attempt to extend the standard model. We are adding some new particles, some dark particles. And so is this the main motivation of our project. So where should we search for these particles? Well, a good place to start is the region of so-called long-lived particles, as it's not explored very well. And so we assume that dark particles could be long-lived particles. And if they're long-lived, they should leave significant exotic traces in low-level data. So we should search low-level data for anomalies. So what we will do? We will generate large amount of data using PTA Monte Carlo code and Dark-Scholar model, and we will generate data for background. Then we will take the existing, for beginning, we will take the existing our autoencoder model. Autoencoder is basically the model which compresses data to some latent space and then reconstruct it from this latent space. So we will train this autoencoder on background sample. Then we introduce anomalies in this background sample, and then we compare input and output data. And so if they somehow distinguish, this will tell us that there are some anomalies. And so then we analyze signal-to-noise ratio and analyze some other metrics. And if everything goes planned, we probably will take some more sophisticated models to do the same task. And basically this is it. And yes, this model, it's meant to run on the hardware which HLT high-level trigger 1 is currently running on. So it is cluster of NVIDIA graphics card. That's all. Thank you for your attention.
Thank you, Dmytro. Any questions for Dmytro? All right. Next up is Sam.
One second, sorry.
Sure.
Hello all, my name is Sam Kelson, and today I'll be presenting my project proposal for the development of experiment-specific data schemas for Coffea. So a little bit about me. I am a rising senior at Brandeis University, so class of 2025. I am a double major in physics and applied math, and a computer science minor. As far as previous strategic experience goes, I have been studying the sensitivity to longitudinal vector boson scattering in same sign WW events at Future Hadron Colliders at the Brandeis Physics Department under mentor Aram Apyan. And currently, I'm under the mentorship of IRIS-HEP fellows Lindsay Gray, Nick Smith, Matthew Feichert, and Garrett Stark. So what is Coffea? Coffea is a columnar object framework for effective analysis, and is a Python library designed to integrate various essential components for conducting analysis at HEP experiments utilizing the scientific Python ecosystem. So instead of using Root's ecosystem, we want to use Python's ecosystem as it can be more friendly to new users, and it can be familiar for people who are incoming just because NumPy is a lot nicer than getting used to C++ or Root's frame analysis stuff. So another main difference is a paradigm shift from the event loops of Root's R data frame, or examples of Root's R data frame, to a columnar approach, where instead of an outer loop and a giant event loop that goes through all the events one by one, we have a more inner loop that goes through the arrays of the different columns of our events. And so we kind of transform each event and as it goes through the analysis. And so this is kind of a paradigm shift to more array programming, and it's more familiar if you're coming from NumPy, which a lot of people are, because that's what's taught in a lot of our schools. Furthermore, Coffea is highly scalable in the Python HEP ecosystem, and it natively supports a task scheduler called Dask, which is a very popular task scheduler, and it's better than using just basic resource provisioning systems such as Condor, as it allows you to more effectively use the resources you have instead of Condor, where you might finish a job and it's already done, you lose that node. You can use Dask to keep those nodes and keep them working, so you're using your resources better. And so by harnessing modern distributed computing technologies such as Dask, Coffea enables seamless scalability of HEP analyses from initial testing on, say, a laptop to maybe one file to a large deployment of to a large computing cluster such as a supercomputer without really modifying the code. You're really just writing new Dask files or Dask configurations, which is pretty simple. So natively in the background, Coffea uses awkward arrays. And awkward arrays come with a very nice utility such as awkward array behaviors. Now this utility kind of borrows from object-oriented programming ideas, where a data structure is defined by the information it encodes and the way it can be used. So an example is a Lorentz vector. So say you have a list of Lorentz vectors. Yes, each single Lorentz vector is just 4 numbers, 4 floating point numbers, but there's more to a Lorentz vector than just the numbers. You want to be able to transform and scale and boost those Lorentz vectors. And so at some point you might have to create a new class to define a Lorentz vector, but instead of that, awkward array has this really nice feature where the developer can encode Lorentz vectors, say this is the Lorentz vector, this is how it's going to be transformed, and then the user can use it as a Lorentz vector, which is more familiar to any scientist who's using that structure. And so, for example, any root file that you maybe enter into your analysis, or any N-tuple that you enter into your analysis, is going to contain maybe a list of Lorentz vectors. And so we want to be able to recognize those Lorentz vectors from that data structure, that whatever's coming into our analysis. So that's where the next part of my goal for my project comes in. So as Coffea continues to be adopted across a spectrum of HEP experiments that employ diverse data formats, such as CMS and ATLAS, they use different data formats, PHYSLITE and Nano AOD. Maintaining experiment-specific schemas that prioritize user-friendliness and performance becomes increasingly complex. So the primary objective of my project is to address these challenges by improving the developer and user experience around Coffea schemas. So for each particle physics experiment we have a specific data format And Coffea aims to be used with any particle physics experiment. So we want to be able to support a wide variety of data formats. So then initially the focus will be on updating the current ATLAS-specific PHYSLITE data schema and providing validation tests to make additional changes easier to support. Furthermore, Coffea is focused on scaling analysis workloads across computing resources, so there will also be some additional benchmarks on how fast each of these analysis is running on different data formats, as they should be approximately similar for same size files. So in conclusion, the project deliverables are as follows. Firstly, we have an update to the ATLAS PHYSLITE schema. Second, we have a test suite for future data schemas. Third, we have a community reference benchmarks for Coffea scaling, so people can kind of know how fast their analysis is running, if it's running too slow or too fast. 4, we have an improved public documentation for new developers. And finally, general schema improvements, time permitting, maybe a refactor, allowing users to define their own schemas, as right now it's kind of a developer-only thing. Thank you for listening. Are there any questions? Sure, go ahead, Samuel.
Hi, I'm just curious. So, is the end goal with Coffea to like replace root, or to be used like as an alternative, or is it to be used in conjunction with root?
I think it's kind of user dependent. Right now, Coffea is still in development, still pretty early stages. I think the general idea is to make it like an additional thing. So far, though, I've used Coffea for a month now, and I've also come from a background of using root. And I much prefer Python ecosystem and Coffea. It's been a lot easier to write. Stuff that took me months to write in root took me a week to write in Coffea. And so just personally, I prefer the Python ecosystem, and that's more similar to what my brain works with. But I think it's meant to be up to the user, and it's just another option that can be used with any analysis, where root, there's some stuff that can only be used for specific experiments, a lot of experiment-specific software tools. And so this kind of aims to be like just a general tool that anyone can use for the base analysis steps.
Great, that makes sense. Thanks.
Any other questions?
Any other questions for Sam? Thank you, Sam. Nice talk. Next up is Dennis.
Hello, can you hear me?
Hi. Yep.
Oh, just a moment, I will share my screen.
Great.
Okay, can you confirm that you see my screen?
Yep, just fine.
Yeah, we can.
Thank you. Hello, my name is Denis, and today I want you to present a little bit introduction talk about my project under title Analysis Grand Challenge with ATLAS PHYSLITE data. And it is funny because Analysis Grand Challenge already been mentioned by Valerii, and PHYSLITE data was mentioned by Alexander, so I do not have to spend too much time on introduction of that, just a few keywords. Okay, in this project I'm gonna to do analysis grand challenge, and this grand challenge is dedicated to test how good input-output from the PHYSLITE data format working for existing Python ecosystem, which include Coffea, which was described by some, and as an example, I gonna to use data of ATLAS collaboration, which is which must be open data collected in 2015, and basically this analysis grand challenge must be based on already existing Grand Challenge for CMS data, and here is the link for the detail. PhysLite data was already mentioned, but I also want to add a little bit for that. The reason for developing this data is for optimization of data processing, which is required by high luminosity updates, where we will have much more data, and it is unskimmed and monolithic. It contains already calibrated objects, and these objects are loosely preselected. And I already mentioned that data is which I will use. It's measured by ATLAS collaboration, and it is proton-proton collision data, and they are accompanied by corresponding Monte Carlo data, which and this data can be found by this link and with supported material by this link. And we as a physicist wanted to see something physical in our work, and basically analysis grand challenge must to have something physical, so that physicists who do data analysis also can use this. And in our case, it is analysis of proton-proton data. Analysis of or reconstruction of T-bar quark pairs, which created in proton-proton collision. Of course, the project is not about data analysis, the project about testing the software. But still, we will have some a little bit data analysis, basically some cuts on parameters of the product of decay, and we look at the basically my work is not finalized, but if we rely on previous analysis grand challenge with CMS data, we must look at the event which have one lepton and at least two jets, which is B tagged. And in the result, we want to have some visual data in such a way that our work can be a nice example for physicists who going to use this PhysLite format in their research, so that they can do their research and obtain some visualization for publication. Basically these two plots is it's from the same previous analysis, already existing analysis grand challenge with CMS data, and it was this analysis was performed by Alexander, and we want to have something similar at the end of this project. And the timeline of this project, starting with, let's say, for me to get used to the software which is used to analysis grand challenge of CMS data. After that, I'm gonna to make the analysis grand challenge with ATLAS data, with this PhysLite data format, with newest version of that data format, and after that wrap up and clean everything, write documentation so that it can be useful and easy for other people to look at this and use it as an example. And where we are now. Currently, very sadly, but this key factor ATLAS data measured physical data, they are not published yet, but they're going to be published very, very soon. But for now, I'm using Monte Carlo data just to make sure that other part of software works, and prepare everything for the real data. And a final deliverable of this project, it must be code, which must be public and reproducible. Code of this analysis can challenge implementation. And that's all. Thank you for your attention. If you have any question, please ask. I will be happy to answer. Yes, we have a raised hand, please.
Hey, yeah, thanks, Dennis. That was great. I have a bunch of questions. I'm sorry. So, on slide 3, if you wouldn't mind flipping back to that.
Yes.
Thank you. Okay, so to throw all of the questions from this slide at you at once because they might be related. What does unskimmed and monolithic mean? And what does loosely pre-selected mean?
Okay. Monolithic is that the data is in one how to say in one piece inside of this file, and there is no to say the truth, I do not really, I expert not in this PhysLite data, but if I correctly understood that there is some way that data is not not repeated many times. If we have some value which occur in a different event, we can use it. We just using link to that. And the same probably with loosely pre-selected. If I see the Alex is raised hand, maybe Alex can help me with this.
Yeah, hi. There's a bit of history behind this in how Atlas used to do things, which comes like way before this project. So Atlas used to have many different, very similar types of data formats that we've been using sort of in Run 2. That all did very similar type of things. So there was some duplication, and this PhysLite has been an effort to move away from this, to have a single format that works for many use cases without lots of duplication. So here this is meant sort of in that context as a single format for everyone to use, as opposed to having lots of very similar types. So that's the monolithic part here. And then in order for everyone to be able to use it, the skimming part is effectively referring to removing events. So if you care about single lepton events and everyone using your same format cares about those, then you can already filter for that. That doesn't work if you want your files to be usable by everyone, because some other analysis might not care about a single lepton selection. So the files need to be able to capture also all the events that everyone might want to suggest, or at least a large amount of people, because there will always be analyses that cannot be using this format. So there's other options available, but this is sort of for mainstream type analysis meant to be as the format that works.
Okay, I think the only remaining confusion that I have here is the words unskimmed and loosely pre-selected to me say two very different things.
Yeah, I think the skimming is meant on the event level in terms of which events you filter out, and the object pre-selection is meant on the objects within an event. So there's some requirements on the objects within an event where you clean out things that you will never be able to use for analysis in these kind of cases anyway. So the sort of content per event is smaller, but we don't remove events that you might want to analyze. So I think that the skimming is meant on a per event, and the pre-selection for the objects on a within an event level.
Gotcha. Okay, thank you so much. I did have one more question on slide 4.
Yes, please.
And this one might, again, be, I know that this isn't really something that you've had a whole lot of time to dive into, but do you know what kind of algorithm is being used to build your jets?
These jets, okay, if we use Monte Carlo data, I do not really dive deep in. Sorry, or do you mean reconstruction data
Yes.
from reconstruction jet from the data from the rough data measured by detector? Well, I admit I do not really so much big expert in this.
No, that's okay. I was just curious. Thank you so much.
It's Antiquity 4, I think, for these.
Gotcha. Okay.
All right. Thank you, Dennis, for the talk. Thank you for the assist from Alex. And there's another comment from Matthew in the chat, so I might answer some of your other questions too.
Yeah, I basically am just concurring with what Alex was saying. So
thank you both for the assist. All right, that's all for today. Thank you all for coming. Thank you to all our fellows for their presentations and their mentors for their mentorship. We have another round of them next Wednesday, which I'll send around an announcement. But that's it for today. So thank you all.
Great, thank you.
Sounds fine.
Thank you. Bye.
Thank you. Ciao.
Yep.